И она меня спросит, чем открыть.
Да.
И я возьму вот эту камеру синий.
Да.
Все, ну пока не буду.
Можно уже, в принципе, уже выпущено.
Просто тогда все наши разговоры.
Ну и можно микрофон отключить. Пока все равно пока никто не пришел. Так, пришло 2 человека. Девушка.
Так, есть ваше имя.
Да, девушка подключили микрофон, подключили камеру. Вот. Включили камеру.
На кого микрофон повесить? Микрофон.
Микрофон?
Последний раз или?
Слушай, а я уже надоел, да?
Нет, совершенно нет.
Я вот тут ехал и думал. А? Нет, дело в том, что я ехал и думал, вот то, что я вам рассказываю, это как бы у нас такой семестровый курс для старшекурсников.
Понимаю.
Я пытаюсь его очень так фрагментарно получается, но, по крайней мере, если я вот сегодня я наконец начну рассказывать уже про квантовые версии этих скобок, про квантовые версии, то есть у нас будет квантовая алгебра функций, а потом как бы объект в виртуальном пространстве — это алгебра уравнений отражений. Вот про них бы я хотел поговорить, но мне минимум 2 лекции еще точно.
Нормально. Это, в принципе,
то есть я в декабрь залезу.
Ну ничего страшного. Да, кстати, если ты, значит, тебе полагаются какие-то небольшие деньги за эти лекции.
Ну, я не рассчитывал, если это сопряжено с какими-то трудностями, то ничего страшного.
Надо подойти сюда в какой-то день. Я не знаю, я попрошу их, конечно, чтобы они до вторника дотянули. Вот в следующий вторник, я думаю, подойти, назвать фамилию.
А, хорошо. А куда подойти? Вот ну, или прямо, созвонимся.
Тут прямо за дверью справа есть.
Вот сюда, да? И сказать, что я такой-то, дайте мне деньги, да? Здорово.
Я не знаю, мне нужно так устроить, какие-то символики.
Ну, сам понимаешь. Так.
Кто выступает?
Ага. Так, мы должны еще что, дождаться компьютера, да?
Да. А уже можно подключать, да?
Да, в принципе, можно. Так, эти часы правильно идут, да?
Да.
Я буду за этим следить до 7, чтобы наши китайские друзья не умучились. А если они не пришли, то можно и по-русски говорить?
Нет.
Лучше на английском, да? Можно начинать? Окей.
Дайте секундочку, пока. Через пару минут начнем. Давайте дадим этим товарищам появиться. Пока. Так. Кто мой телефон? Это кто? Это моего Саша, кстати, не видит. Сюда своим телефоном. Так.
А вот эта камера, значит, работает независимо от компьютера. А, его надо включить, да?
Он уже включен.
Сейчас достану. Ой, сломать это все.
Ну да.
Красненько, да?
То
написано.
Как его выключать тогда? Нужно нажать?
Нет, вот тут вот сверху, нет, сверху такая.
Не.
А, нет, надо открыть.
Да,
Открыть этот и нажать кнопку.
Подержать, да.
Да.
Хорошо.
Все, ну что, shall I start? Oh, it's better to wait.
Микрофон, вы включили микрофон, да, уже, Паша?
Микрофон подключен в YouTube, который.
А ваш, который включите его тоже?
А, мой, да. О, пардон. Так, ну послушай, вот слышно что-нибудь, что я говорю или нет? Или не слышно? Нет, не слышно. Подключить. А у меня есть?
Есть, конечно.
Так, у меня, что у меня должно быть включено? Выход в интернет, да? Или что?
Нет, давайте.
Давай.
Так, где, покажи сначала это самое, его, сам твой зум.
Вот он.
Так, давай, а где он? Ты отключился, что ли?
Да нет, он только что
тогда?
был.
Дай я посмотрю.
Ну давай опять включимся.
Очень странно.
Он только что был, и там был
Вот
этот вот зачеркнутый микрофон, я его нажал.
Что заработало?
То есть надо нажимать на это беленькое поле, да? Ой, ну ладно. Окей. I can start. Last time we introduced some quadratic brackets on the algebra of functions, on matrix algebra, the Sklenin brackets and the Semyonov-Tinshansky brackets, and considered some of their classical properties. Today we at least come to the quantum versions of these algebras, and we will start from the Sklenin brackets. The result, and I recall you their construction. So the matrix T of generators and the corresponding bracket is of the form T1, T2. It means two arbitrary generators is equal to just a matrix commutator T1, T2. Here we have the so-called classical R matrix. This indices AJ runs from 1 T, this big N, and this is N squared times N squared matrix, which satisfy the classical Young-Baxter equation, and the property, this property guarantees the antisymmetry of this construction, and the classical Young-Baxter equation gives us the Jacobi identity for this bracket. And let me restore once more the two-dimensional case where I have written A, B, C, D. And for example, the brackets of AB, from this it is not difficult to find that it is equal to AB. And all other brackets are of the same structure. Here we have some quadratic monomial in generators. At this stage we have an obvious problem with quantization. For example, the standard procedure for quantum mechanics, where we have, for example, the constant brackets Qi, Pj is equal to delta Ij, we come to the quantization in the form of Lie bracket. We have a new algebra generated by non-commutative generators. And here we have the unit element of our algebra, and we change the Poisson bracket for the Lie commutator. And here I can try to do something. Let us postpone the problem of ordering. For example, if I take for this one A, B minus B, A is equal to H, A, B. For example, let us put this by definition. I see that the commutator is not natural construction here, because I can unite these two elements and find the relation like 1 plus H plus maybe something else here, A, B, is equal to BA. So this is some indication that we should have something, not a commutator, but another some associative structure on the quantum algebra. And indeed, I give here the reference where you can find the detailed presentation of the quantization of classical semi-simple Lie algebras and groups. This is a paper written by Fadeev, Takhtajan, and Reshetikhin. This paper was published in Algebra and Analysis, and the title is the Quantization of Lie groups and Lie algebras. It can be found in Russian and in English translation. The quantization of Lie groups and algebras. The quantization means the quantization of functions on Lie group and the quantization of the corresponding dual objects. And this is a simple example. And the true quantization of the Sklenin brackets gives us, I put here the hat in order to make a difference between the classical generators and new non-commutative quantum generators. A, B, C, D. I have four elements here also, and the elements A, B, C, D, they are the generators of associative algebra. So our quantum algebra is a words constructed, monomials constructed from these elements, and the final linear combinations of these monomials. And also I should take into account the following relations among these elements. The relations will be precisely in this form. AB is equal to Q BA. They are not in the form of commutators, but AC is equal to Q CA, AD minus DA is equal to lambda BC. The Q is a complex number which is not equal to 0, and lambda denotes the difference, Q minus 1 over Q. Three relations of this type and three other relations, B and C commute with each other. And CD, Q, DC. How to find the quasi-classical limit? Let us introduce a new parameter, H. Just a logarithm of Q, or in other words, Q is equal to e to the h, 1 plus h plus O at h. And in this case, we can restore the classical Sklenin brackets as it should be for the quantum algebra, namely, if I consider from the first relation, let me write A B minus B A, it is equal to Q minus 1 B A. So if I divide this by H, A B minus B A, let us divide it by H, and let us expand this parameter Q like is written there. I find that it is equal to BA plus H, some other elements. So this non-commutative product tends to the product of commutative elements when H tends to 0. So I find that it is equal to AB as it should be. So expanding this parameter in powers of H, I find that the Poisson structure in the quasi-classical limit is indeed the Sklenin bracket. And in order to generalize these relations to the higher number m, which is not equal to 2, let us introduce the 4x4 matrix R of the form Q, the parameter lambda 1 over negative Q. This is 4x4 numerical matrix. So the relations of this type six independent relations can be encoded into the following matrix equality. It turns out that if I write the following matrix equality, this is equality of 4x4 matrices. So here I should write this 4x4 matrix. This product, let me write explicitly, A squared, AB, BA, B squared, AC, AD, BC, BD, and so on. CA, CB. This is also a 4x4 matrix. And on the right-hand side, I have the same matrix structure and R12 again. If I multiply this matrix with non-commutative elements by this numerical matrix, I come to the 4x4 matrix with some non-commutative entries. And the same I will do here and find another different 4x4 matrix with non-commutative entries. Then I should, if these matrices equal to, should be equal to each other, I should equalize any matrix elements. And from these 16 matrix elements, I have found only 6 independent relations which precisely coincide with these relations. All other 10 relations will be identical consequences of these 6 independent relations. So, in what follows, I will consider this form of my relations, and this is a reason why such an algebra can be called the quantum matrix algebra, because its generators can be organized into the matrix, and the permutation relations among the generators can be written in the form of equality of some matrices with non-commutative entries.
T1 hat is what kind of matrix?
We have the same notations as we established at the first. T1 is the element of endomorphism of C2 tensor T of the form E1A tensor A tensor T hat 1A. This is T1. And T2, this is 1. This is a 2 by 2 unit matrix over EIJ T hat IJ. T hat, it is these elements. So, this is by definition. And when I multiply these elements, I just obtain this matrix.
Tensor product is taken over some
Over the complex numbers.
complex number.
Yes. This definition is true for any algebra, commutative or non-commutative. This is our notation. So it is easily to find that when I multiply these two objects, I'll obtain precisely this object. T1, T2 is also T1, T2 belongs to the endomorphism of C2, tensor 2. This structure is defined by the first two factors over my non-commutative algebra T, to which belongs these generators. So this is a 4 by 4 matrix, and the matrix elements are defined by the last factor of this 4 by 4 matrix. Okay, such an algebra will be the algebra if R is Drinfeld-Jimba R matrix. This is only an example of all possible R matrices, and such an algebra will be called the quantum algebra of functions over the group SLN after some factorization of this algebra over the central elements, which is called the quantum determinant. We will speak about this a little bit later. The dual object, the dual algebra to this non-commutative algebra is a quantum universal enveloping algebra, dual object, UQ of SLN. These non-commutative algebras belong to the class of so-called quantum groups. Actually, this is the algebra of quantized functions over the quantum algebra, or its dual object, which is a quantized universal enveloping algebra.
The capital R is the matrix which appeared last time when we spoke about the scanning.
Yes, yes. This is a good comment because from now I would like to speak a little bit more about R matrices and about the Hecke condition. This is not so important for the RTT. Such an algebra is shortly called RTT algebra because there is a lot of examples of R matrices which are not Drinfeld-Jimba ones. And in such case, this RTT algebra cannot be treated as the algebra of some group. It is just non-commutative algebra with some Poisson structure. And let me speak about the very important object which stands behind these R matrices. This is a so-called Hecke algebra. In the theory of quantum groups, the Hecke algebra plays the same role as the algebra of symmetric group plays in the theory of, for example, universal enveloping algebra U-SLN. It is especially in the representation theory of quantum matrix algebras, we need the properties of Hecke algebra. So I shortly formulate some properties of this algebra, and its representation, R matrix representations, will give me the examples of R matrices which is standing here in RTT algebra, in reflection equation algebra, and so on. And I would recommend you very good review of this topic, which is written very instructive, very simple, and very shortly. This is a paper lecture on Hecke algebra. Lecture on Hecke algebras, written by Oleg Gievetsky. And Pavel Pyatov. This review can be easily find out in the internet. It is published somewhere. I do not precisely remember where, but it's not difficult to find it in our archive. So all my presentation will be based on this paper. So let us consider this algebra. I will consider the type AN Hecke algebra. Because this algebra is defined for any series, and there is affine Hecke algebras and some other varieties, but we will consider the simplest variant of these algebras, type A Hecke algebra. It is denoted by Hn of Q because the Hecke algebra depends on the non-zero number Q. Let us consider it as a non-zero complex number. Sometimes it is convenient to treat this Q as a formal parameter, and we will consider the algebra over the ring of polynomials in Q, but it is not a mistake to consider Q as a fixed complex number. This is a finitely generated algebra, generated by the unit and n-1 generators Hn of Q. This is 1, G1, G2, Gn-1. Such generators, and these generators satisfies we can consider this, this algebra as a factor of the free tensor algebra generated by the space and dimensional space over the following relations. The braid relations gy plus 1 gy is equal to a plus 1 a plus 1. And minus 2 here, because not all. Another one. They commute if their numbers have a sufficient distance between them, namely if the difference greater or equal to 2. So non-commutative generators only those which numbers differs by 1. And the last relation, these relations, if I also suppose that my elements are invertible, they generate the so-called braid group. And now I'll consider the group algebra of this braid group. In general, this is an infinite dimensional group, even for finite numbers of generators, and infinite dimensional group algebra. But if I put the polynomial relations of the form squared is equal to, this is a unit element of my algebra. In what follows, I will not write the h here, but this means the unit element plus q minus 1 over q. Here we first time encountered the number q. Then this algebra will be finite dimensional. In case of q is equal to 1, I'll just have an algebra of symmetric group, because these elements can be treated as a transposition of two neighbors.
So if you look at the first relation and the second relation, I believe don't you need cyclic order? I mean, if you when I plus 1 is greater than n minus 1, don't you just take gn plus 1 equal to g1?
No, I would not.
So don't do this.
This will be somewhat different.
So that will probably
thing.
correspond to some other root type, right?
Yes, yes.
To b.
This is just a Coxeter diagram corresponding to the AN. If I have a loop, it will be another object. Okay, so which properties of this algebra I could mention? First, Hn is finite dimensional algebra. And dimension of Hn of Q is equal to n factorial. Let us define the element, for example, sigma aj for a greater or equal to j. And n in the following way. If the indices coincide, it is unit element. If a is equal to j. And if a strictly greater than j, strictly greater, and it is Oh, no, 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 is equal to. And it is equal to, let me precise. A minus 1, A minus 2, till the A, if A is greater to J. Let us introduce such type of objects. Then, the linear basis this means that any element, this is a generator, pardon, no. J, here the generators of my algebra.
What is sigma ij?
This is a specific monomial constructed from the generators of my algebra.
So these are the bases. This is the basis.
This is a linear basis of this algebra. This is a generators, so I should construct some words, some monomials of the generators, and
The claim is that the number of elements in this basis is equal to n factorial.
yes, yes. It is not a basis. Still, I will formulate the form of basis in terms of these monomials. I will not prove this because it will take the time for us, but I just illustrate this by a simple example. The linear basis of Hn is formed by the following elements: sigma 2a2, sigma 3a3, sigma n an, for all possible A2, A3, AN. We should keep the order because this is non-commutative generator. We should keep this order in this form, and we should take into account that some elements may be absent here because, for example, if A3 is equal to 3, we have the unit here. So let us write an example for H3. It is equal to 1, J1, J2, with the only condition, the break condition is only 1 here. So, sigma 1, 1 is equal to 1, sigma 2, 2 is equal to 1.
By monomials, so these monomials are described by all possible sequences I2, I3, and so on.
Of all yes. The only restriction is that sigma k is not greater than k. And then we should take this definition. Let us consider what we have here. Sigma 2, 1. Here we have only one, this element. It is equal to J1 due to such definition. Sigma 3, here we have two elements. 3, 1 is equal to J2, J1. Again, if I is equal to 3, so we have G2 till G1. And sigma 3, 2 is equal to J2, J2. Okay? So I have 4 elements, 1, 2, 3, 4, and another one, sigma 2, 1, sigma 3, 3, 1 is equal to J1, J2, J3, J1, and at last sigma 2, 1, sigma 3, 2 is just J1, J2. It differs from this. So I have 6 monomials. 6 is equal to 3 factorial. And it can be easily seen that there is no other monomials independent of this, because also I have the quadratic relation J. These all possible combinations in my Hecke algebra. If I multiply these elements by any generator of my of J1 or J2, then I either get some of these elements, or I apply this property and get the linear combination of these elements. This is a linear basis. Of course, it is not very convenient basis, because it is rather difficult to imagine all possible combinations of such type monomials. And we will use the following very important property. Up to now, I say about the parameter Q, the only thing, it should be non-zero complex number. But now let us restrict slightly the range of this complex number by the following requirement. Let us define the following object. For any integer k, I can introduce its q analog, kq. By definition, it is equal q to the kth minus q to the minus k divided over q minus q minus 1.
So what is the purpose of this consideration in Q? What are we going to do with this? So you give the description of linear basis, in Hecke.
It's just for the general education, because I will introduce another linear basis, the basis of constructed from primitive idempotent indicated by the partitions. And this will be much more convenient and much more useful basis for us. So let us define such a fraction. Q is not equal to 1. For a moment, this is a Q number. And we will say that Q is generic if kq is not equal to 0 for any q, for any k. So the q is not a root of unity. It means that q to the k's power is not equal to 1 for any q, for any k. Q is not a rational point of the circle. If we restrict our parameters q by this requirement, then we get that any q number is not equal to 0. And it can be easily seen that when q tends to 1, we have just a usual number, k. We can divide this expression over this one and get precisely that this is q to the minus k plus 1 plus q to the minus k plus 3 plus and so on plus q to the k minus 1. If we divide this, explicitly divide the numerator by denominator, we can get this expression, and we get such a limit. If this is true, then Q is called generic. And very important property for us is that for generic Q, the Hecke algebra is semi-simple and isomorphic to the group algebra of symmetric group. Its dimension is n factorial. It's good, but because the group algebra of any finite group is semi-simple, then if Q is generic, then Hn of Q is semi-simple for any n. And Hn of Q is isomorphic. Well, here's a permutation group. If so, if this is a semi-simple algebra, then according to the Wedderburn-Artin theorem, finite dimensional semi-simple algebra is isomorphic to direct sum of matrix algebras. And then if Q is generic, we have can be written as the sum of the lambda is not it's not let us take another mu. This is a whole partition of a integer n, and here I have.
It seems that the first statement about simplicity follows directly from the second statement about this isomorphism, right? Because the group algebra of finite group is always semi-simple.
But no, I do not agree with you. If this is semi-simple, that is isomorphic to the direct sum of matrix algebras. But why it is isomorphic to this concrete algebra?
If we know that
These algebras are isomorphic, then it.
that's what I mean. The second
Yeah.
statement is that it is isomorphic to the group algebra of the finite group. And it is always semi-simple.
Yes, of course. I can write this isomorphism explicitly over C. What does mean d mu? This is a number of standard tables corresponding to the diagram mu. If mu is a partition of n, then mu is a finite.
dm is the Young table. dm is a Young table.
dm,
Yes.
yes, Young table. I consider the mu 1 is greater or equal to mu 2 is equal mu s. The sum is greater to 0, the sum of these elements is equal to n. This sequence is called the partition, and we put into correspondence to this partition a Young table, a Young diagram, and if I put in the boxes of this diagram the numbers from 1 to n, I'll get the table.
So the summation
or
is
tableau.
all partitions, right?
Yes, over all partitions, all possible partitions of n, and the dimension of this algebra, matrix algebra, the dimension of matrix is equal to the number of all possible standard Young tables corresponding to this diagram. I mean the Young table standard if the numbers increases from left to right and from up to down. For example, for H3, I have 3 possible partitions which can be encoded by the Young diagrams of this kind. This is a partition 1, 1, 1.
What do you mean my matrix is sub d mu? D mu is
D mu is a number of Young tables.
what is mu is a partition?
Mu is a partition. To the partition, I put into correspondence the Young diagram, and then I'll get a lot of tables with of the same shape corresponding to the diagram. And the number of these tables is d mu.
So a table is just the way you put numbers 1 to n.
Yes, yes, yes. Here I have 3 partitions, 2, 1, and at last this one, it is just 3. And here I can, then I should place the numbers from 1 to 3 into the boxes of this diagram. Here I have only one possible standard tableau, because I should have increasing numbers from up to down. Here I have 2 possible 1, 2, 3, 2 possible tables. 1, 2, 3. Here D is equal to 2. And here I have again only one. Possible table. 1, 2, 3. Okay?
So the right side is always, right side should be always bigger than left, and the down.
So I have that H3 is divided by the one-dimensional matrix, matrix 1 corresponding to this one, then two by two matrix, and then again here I have 4 elements, 1 plus 1, 6 elements in my Hickey algebra. The number of these tables can be easily calculated by the Hooke formula, so-called Hooke formula. By the way, this Hooke formula is very well known in the theory of symmetric group, but the proof of this formula is not easy. But for the Hecke algebra, it can be proved in a much more simple way. And this proof is presented in the paper by Agiyevetsky and Pyatov. And then, taking the limit q to 1, we get the corresponding Hooke formula for the symmetric group. And the formula is the following. If I have a Young diagram and take some box inside this diagram, I should write the following 2 lines from this chosen box till the end of its line and down till the end of this column. And then I should calculate the numbers of boxes which is crossed by this line. This element A, значит, hook HA is a number of these boxes, the number of crossed boxes. For example, the hook of this element is equal to 1 because it is the last element of the line and the last element of the column. Then the number of, if this table corresponding to the mu, the number of possible tables which can be constructed from this concrete partition is the following fraction, n factorial divided by the product over all alpha over all boxes of my diagram, the corresponding hook of these elements.
This actually encodes an element in the center of the group algebra of the symmetric group, or the permutation group. So in the center, what you have done is just a description of the center of the group algebra of symmetric group.
Yes, I will formulate the corresponding structure of the center of this Hecke algebra, and they can be reformulated in some generators of the center of symmetric group in the approach of Vershik-Okunkov, for example. This is a Hooke formula. For example, if I take this one, so n is equal to 3, so the number of possible tables is 3 factorial divided by product of all hooks. Here hook is equal to 1, here hook is equal to 1, 2, 3, 3, and hook here is equal to 1 again. So it is equal to, and indeed I'll find 2 possible tables. And I would stress that this formula it is not easy to prove this formula. It is even hard to understand why the n factorial should be divisible by the denominator. Why it is an integer. Not speaking about why this integer is equal to the number of tables. But the direct proof is given in the paper of Agiyevetsky-Pyatov for the q is not equal to 1, and then it can be obtained for the symmetric group. Okay, what about the center of this? Okay. Of course, for the counting the standard tables, there are rather different, a lot of different formulas. But from my taste, this is one of the simplest formulas. It's very effective. For all concrete examples, it's very easy to calculate this number. Okay, let us introduce the following set of very important elements, the so-called Eutzes-Murphy elements. Uses Murphy elements of Hickey algebra is introduced by the following relations. G1 is equal to 1. G2 is equal to J1, 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 or J1 squared. And Jk plus 1 is Jk, Jk, Jk. Such a recursive procedure, recurrence procedure. So I have J1, J2, Jn elements, and very simple calculation say us that all these elements commute with each other. This is a commutative set of elements, commutative set. And these elements generate the maximal commutative subalgebra inside of our Hickey algebra Hn.
So
If I take all possible products and all possible linear combinations, I produce the commutative subalgebra, and this will be maximal commutative subalgebra.
center.
Huh? Not center. What about the center? Any symmetric polynomial in these variables belongs to the center of this algebra, and if I consider the element Zn is equal to J1 plus J2 plus Jn, then these elements generate the center of Hickey algebra. Any central element of Hickey algebra is a polynomial in Zn. Zn, polynomials in Zn generate the center of generate the center. And at last, an important construction of the linear basis, which is which corresponds to the direct sum of matrix algebras. I'll construct the set of primitive idempotents. There is a set of primitive orthogonal idempotents P lambda A. I will denote this idempotence by these elements, which are polynomials in the Euclid-Murphy elements. They can be constructed as polynomials of these commutative elements. Index A here runs from the partition, lambda is a partition, and the index A runs
The center is just generated by one element. The center is generated by one element. The center of the Hickey algebra is generated by the sum of uses.
Yes, and any symmetric polynomial in J is also central. It is.
Don't see this because don't see. Here we just have one generator,
Yes.
and here we have. At least it seems so. We have many generators.
Many
All symmetric polynomials of uses Murphy elements.
because these elements, for example, if you take, for example, the square of this element, you should remember the relations in such algebra.
So it turns out that actually all these elements are, all these polynomials,
They are not central because they are not symmetric.
No, symmetrical, so sort of primitive.
They belong to the commutative subalgebra, yes. They commute with each other, but they are not central.
What do you
Primitive, it means that it cannot be presented as the sum of idempotence of the smaller size. The sum of all these elements over all partitions of n and A running from 1 to d lambda is equal to 1. And p lambda A na p mu b is equal to p lambda A delta mu lambda delta A b. They are orthogonal to each other. And each primitive idempotent belongs to the corresponding matrix algebra in our direct sum. They are orthogonal to each other. Their sum is equal to 1.
So can you repeat this, please? So there is a set of primitive orthogonal idempotents.
Yes, this property means that this idempotence, the square is equal, the square of each element is equal to this element. And the product of different elements is equal to 0. And the sum of these elements is the unit element of my algebra.
They are indexed by what? They're indexed by diagonals.
Yes, for example, P 1, 2, 3 and P.
Lambda A. What is lambda A?
A calculates the numbers of tableaux. For example, for lambda is such a diagram, there is two possible tables. Two possible tables corresponding to...
What is lambda? What is
lambda is a partition or Young diagram. And this lambda is a partition of n.
So there are not just, probably it's better to write lambda comma A because A is just a variable, is just an index.
I mean, lambda A is a Young table of the shape lambda. For example, if n is equal to 4, I'll get, for example, such kind tables, such kind partitions, and at last 1, 2, 3, 4, 5 possible partitions. But here I have only one. D is equal to 1, only one table, only one possible table. Here I have 3 possible tables, so 1, 2, 3, 4, and so on. Here I have D is equal to 3, so for the partitions of such shape, I need three different tables, so A comes from 1 to 3. Here I have only 2 possible partitions, 2 possible tables, 1, 2, 3, 4, and 1, 2, 3, 4. Here A runs from 1 to 2. Here again 3 possible tables, and here again only 1. So, P lambda A is an explicit polynomial in Jutes-Murphy elements.
So is there a description of this polynomial?
In the paper of Г.И.Шарыгин, you can find if you like, I can write it, but first I again have no time for this, but I'll write the most important for me, the partition, the primitive idempotent corresponding to the vertical strip or to the horizontal strip, because in my structural theory of quantum matrix algebras, the representations of these elements will play an important, very important role. It is very simple. I would like to mention one more property, which is also very important in the representation theory of quantum matrix algebras. If I consider the regular representation of Hecke algebra by multiplication on the vector space coinciding with this algebra itself, then I'll find that in regular representation, left or right, it is the same, because I will consider the commutative subalgebra generated by Euclid-Murphy elements. These primitive idempotents are eigenvectors of Euclid-Murphy elements. So in constructing the representation of Hecke algebra, it's very instructive to find the basis in which the commutative elements are diagonal. So these primitive idempotents are eigenvalues, eigenvectors of Euclid-Murphy elements, and the eigenvalue is calculated as follows. For example, if I consider lambda A some table, and I take the Euclid-Murphy elements Gk, what should I do for this concrete primitive idempotent? I should find a box where the number k stands. For example, here there is a number k. Then I should take the following q to the content what is the what is written here? This A, this J. So the number k is located in the crossing of eighth column and J road. So this content is two content. 2 by the difference of J minus A.
Sorry. So you take the decomposition of symmetric of your algebra, Hecke algebra, into the direct sum of matrix subalgebra.
Yes.
Then how do you find? So did you claim that the unit?
Yes, I can construct the matrix units and any matrix corresponding to a partition lambda.
How do you describe them in terms of E?
Yes, yes, I can construct the elements E, A, B, which likes P lambda A, P lambda B.
So what is it? What is the law? What is the vertical?
These are some polynomial generators of my algebra, which behaves like P lambda B in multiplication from the right hand side, and like P lambda A under the multiplications from the left hand side.
It's a product of these two polynomials.
No, it is not a product of these idempotents. This there is some. For example, if I fix lambda and it has different tableau, I can transform one idempotent to another one, like in symmetric group, by multiplication on some monomial ingenerators, corresponding to the permutations. Pardon? Yes, yes. So this object is actually, for example, p lambda a multiplied by some monomial. Its construction is explicit. Not a ratio, this is a product.
But what does lambda b do? What does p lambda b do?
Okay.
Sum is the elements you use to multiply.
Yes.
Doesn't it? It means the difference between lambda a and lambda b, isn't it?
For example, if I have a primitive idempotent of this type and the primitive idempotent of this type, there is a relation between these elements. Here I should multiply over G2 minus some constant. Actually, this is this constant depends on the length of way connecting these two numbers, and then it is identically equal to this form: G2 minus const prime. You see, this is an identity. And this object is precisely 1, 2, 3 bar 1, 2, 2, 3.
It's not quite clear what it means, but it would mean that you have two elements, p lambda a and p lambda b, and then there's a
Yes.
procedure which allows you to write down this expression.
Gosha, we have here the primitive idempotent P1, this is let P1, this P2. Here I have P2, and here I should have something which is similar to P1 from one side and P2 from the other side. P12 and P21. In which sense? They, I should PAB na PCD should reproduce the algebra of matrix units BC PAD. And these elements should be eigenvectors of Euclid's method elements from under multiplication from left and right side.
Well, what I have just understood is that there is a procedure which takes elements p lambda a and p lambda b and pairs them so that we obtain some other element represented as matrix unit.
It is written here in an explicit.
It's a kind of algorithm which is a well-defined algorithm. So you can. That's what I understood. I don't quite understand.
Yes, we can construct some monomials in generators which behaves like matrix units, and
sorry, there is some problem with the sound, I'm afraid. I'm sorry I missed this. There was some people complaining about the sound.
Слушай, проблема в том, что у меня сел телефон.
You can take mine. I see. You can take my phone if you want.
But I'm afraid that we should stop now because
say something through mine.
let me
You use my phone to tell something and then you can.
let me finish my presentation by writing the explicit form of the primitive idempotent.
Complaining about the sound.
The precise construction of this primitive idempotent and this matrix units is not very important for us. The important thing is that Euclid-Murphy elements multiplied by these primitive idempotents give the Q to the content of this box. This content is just a difference of the J minus Y. So if I have I just write this is the corresponding eigenvalues 1 Q square Q to 4th power Q minus 2 1 Q2 and so on. So you have you see that J1 is equal has the eigenvalue only 1 because it is the unit elements. J2 have only 2 eigenvalues, Q squared and Q minus squared, because the number 2 can stand only here and only here, and so on. This is.
So since you didn't quite, I'm afraid you didn't quite understand the algorithm which you use to define the elements P1, 2, P1, and so on. So I just guess that there exists an algorithm which will actually give you all the coefficients as powers of sums of powers of certain powers of Q, right?
Yes. Yes.
That's what I would say, but other than that, I'm perfectly out of all reason. Okay, so.
Okay, I will not write the precise form of the
Maybe next time.
idempotent because I will actually need the R matrix representation of this kind, because the definition of GLN type R matrix is based on the properties of these idempotents. So I will start my next lecture from the construction of this Q antisymmetrizer, so-called, and then we will describe the R matrices of GLN type based on the properties of these Q antisymmetrizers. And the Drinfeld-Jimba R matrix, very well-known example, is one of the possible GLN type R matrices.
Okay. So, are there any questions? Are there any questions? Or
Как давно вырубился телефон?
yeah, just the problem. I didn't notice when the phone went off. It seems that the lecturer's phone just turned off.